Hello and welcome to Plant Party. We are doing a plant party today all about grasses for the win. It is hosted by Texas Parks and Wildlife Department, Texas A&M AgriLife Extension Service, and USDA Natural Resources Conservation Service. Plant Party is a quarterly webinar series intended for advanced plant training and fun education. I'm Megan Clayton, Professor and Extension Range Specialist with Texas A&M AgriLife Extension Service. My co-hosts are Tim Sigmund, the Private Lands Program Leader with Texas Parks and Wildlife Department, and Charles Kniper, State Resource Conservationist with USDA Natural Resources Conservation Service. Our door prize donors today are committed to supporting you in your quest to learn more about plants. I'd like to thank Bamert Seed, InView Range and Pasture, Native American Seed, Texas Quail Forever, Renewable Resources Extension Act, Texas A&M AgriLife Extension Service, and the USDA Natural Resources Conservation Service for donating these neat prizes. We'll be moving very quickly through 5 presentations today.
All right, our first presenter today is George Cates. George is a restoration specialist for Native American Seed, where he's been working since 2002. He graduated Austin College in 2006 with a Bachelor of Arts in Environmental Studies. He currently manages Native American Seed Consulting, Land Management, and Native Landscaping Services. He still chips in as needed with farming and production, harvesting, and seed processing operations. His latest endeavors include greenhouse production of rare hand collections and hard-to-propagate native species to add more diversities to their offerings. He has remarkable capacity for looking at problems as challenges to be met and the kind of willingness to learn that is a priceless asset. He loves to teach and share what he's learned through his journey, especially to his son Fisher and the next generation of land stewards. Thanks for kicking off our plant party, George.
I'm George. I work at Native American Seed in Junction, Texas. I do so much stuff that we just came up with a title, Restoration Specialist. Everything I do revolves around native plants, growing them, and finding places and landscapes for them, whether they be small, large, or whatever. So if you have questions after this, you can get me, george@seedsource.com. And so we're going to talk about how cool native grasses are, specifically in 2 applications for lawns and trails. So one of the big drivers of our work is understanding how precious water is. And it's pretty evident that Texas is a droughty place. Now, there are places that get plenty of rain in Texas, and so maybe some of what I'm going to say is not applicable there, but in general, 70% of our drinking water is used on our landscapes. And here's a perfect example. So this is the courthouse in Llano, Texas in the year of 2011, which was an exceptional drought. And here they have green Caribbean St. Augustine grass that is from a place that receives, 100 inches of rainfall per year. And the average in Llano, area is 25. And so the difference has to be made up somehow. And so during this drought in 2011, Llano's only source of drinking water is the Llano River. And people were freaking out because the river stopped flowing for the first time there in a long time. And so they were watering their yards, and they had to put up signs to let everybody know that it was okay because they were using well water. And, really what's the difference between well water and river water? Is like not much. And so I always joke about this sign, where they should put an apostrophe between the E and the L, and we'll water no matter what. So our business started, as a traditional landscape company, install, design, and using all the wrong plants. And this was up in the DFW area back in the 80s, and there was a really bad drought, and all the landscapes were dying because the cities had to shut the water off. And so the founders said, man, this is not sustainable. We need to figure out a better way to do things, and learned about native plants and shifted the whole thing over to native plants, and then eventually over to seed production. So anyway, what about, native grasses and water can we talk about? So native grasses have extensive root systems. And you can see here, there's your lawn grass, your St. Augustine. And so what that looks like, out there in a prairie is something like this. You just have all these massive amounts of roots. And so like what you see above ground is not nearly like what's going on underground. But what that means is that when rain falls, it has somewhere to go. If you have, very shallow root systems and highly compacted soils, the water tends to just run off. And I think a presentation a little later is going to talk about what that means in terms of carbon. So as these root systems grow and shed and die, they leave, cavities in the soil where the water can percolate through. And here where I'm at in the hill country, it translates to in karst systems this crystal clear water. So native grasses also don't, require this additional input of irrigation. Another benefit of having substantial vegetation is that you reduce the heat island effect. So in urban areas, grassed over places can really reduce the heat island. So here a mowed patch is 150 degrees while the unmowed patch is at ambient temperature in the middle of July. Another benefit is the native plants benefit wildlife in a number of ways. This is a grass called Texas cupgrass. It's a mid-height grass. It's indeterminate and it's very attractive to these neotropical songbirds, the painted bunting. So we figured out a while back that buffalo grass doesn't really do all that well by itself as a lawn, and that really native grasses are sympatric and they want to grow together. And so the best alternative would be a blend of some of these species. What we found is that for your typical homeowner, this may be a stretch to have something like this. This is what a mixture of those species look like. It's very typical of, the Edwards Plateau. So we've combined three species that seem to work well together that are tolerable enough for humanity. This is what that looks like. And so, people often want to know what the process is. So there's, always a seed bank that will express itself. There's various ways to go about preparing the area, but, while native seeds are magic, they're not all that magical where they can just make other plants disappear. So you have to do the work to get it prepped, rake out the stuff, and there's your standard operating procedure for applying fluffy native seeds. We like to use these erosion blankets to conserve water. These are warm season grasses, and so they really like to grow fast when it's warm and wet. So, seeding over the winter is not really a good idea. If you want your stuff to establish quickly, you want to do it when the soil's over 65 degrees overnight and hotter. Water can help. This is a very cheap and easy way to do temporary irrigation to get your stuff established. 7 days, 16 days, 35 days in the heat of the summer. Now, often when you're working with seeds, the weeds are an issue, and so you need to be prepared to deal with that. And this is the following spring, so a well-established native turf. And if you're not into that shaggy look, you can mow it. We recommend that you mow it as high as you can and as infrequently as possible. I have some tips at the end on maintenance. These grasses also work well as the foundation of a trail. So, a lot of landscapes will have trail systems in them, and you can use those three grasses to walk on. And despite what some folks may say, they're very good at foot traffic and even vehicle traffic. They will brown out with overuse, but you get off it for a little while and they'll recover quickly. So here, this is the George Bush Library. They have short native grass mix as their walking trails with beautiful flowers and things and some taller prairie grasses on the side. These species are what I would consider to be the best for, short to mid-height meadow grasses and, for use in a trail system. They don't get too tall. They don't look weedy. and they provide a lot of benefit to wildlife because most of the mid-height grasses are indeterminate. So they're producing seeds throughout the growing season. And these seeds are very attractive to songbirds and harvester ants and things. So if y'all want to screenshot this one, go for it. So Texas cupgrass is one of my favorites. I don't have, enough time to show you all of them. So Google is your friend. And again, it's very attractive to the painted bunting. They come here to breed in the summers, and so they're looking for a source of protein, so grasshoppers and spiders and things like that, as for their young, as well as a food source for themselves. So those, constantly shedding seeds are very important to them. So they're a crop pest here at our farm, and I don't know, it's fine for us to share. Hooded windmill grass, it's got a very large range in Texas, mid-height, very interesting. Pink pappus grass, very drought tolerant. So a blend of those together looks something like this. And you can imagine a trail running through there. They're great for, making a meadow. So this would be like a mixed wildflower and mid-height grass meadow in an urban setting. Very sustainable. This is a typical trail that you could make with those grasses. It's kind of what they look like. I myself prefer to incorporate wildflowers into that, but you have to have a foundation of grasses for your meadow. The wider the path, the taller you can make the grass, so you can get into little blue stem and big blue stem and Indian grass. But for most folks in an urban setting, those mid-height grasses are where it's at. So here's some maintenance tips. So infrequent deep watering. So those deep roots require water to be like way down. And so the more often you water and the shallower waterings, that tends to favor weeds. The mowing is important. You can contaminate your planting with a dirty lawnmower. The more you treat it like Bermuda grass, the more Bermuda grass you're going to get. Leaf litter for insect health, and embrace natural succession and seasonal change. So, these are warm season grasses. They go dormant in the winter. It's all part of understanding where you live and being native to that place. Here's some great resources for species selection, identification, range maps. We're on there. If you have any questions, you can call our staff. They're happy to help you no matter the size of your project. And I think I don't have any more time, so I will stop sharing.
Thanks for that great presentation, George. Next up will be our second presentation, and this time it'll be our own Megan Clayton. Since 2010, Dr. Megan Clayton has been a professor and extension rangeland specialist for Texas A&M AgriLife Extension Service and the Department of Rangeland, Wildlife, and Fisheries Management at Texas A&M University. Her responsibilities as a rangeland specialist have her based at the Uvalde Research and Extension Center and include providing support for extension agents, specialists, clientele, and organizations through teaching, training, and providing technical expertise on the management of rangeland resources. Megan's current interests include blending wildlife habitat and livestock range management, small acreage management, UAV drone research, brush management, and youth natural resources education. Her main area of responsibility includes the Uvalde and Hill Country area. Today, Megan is going to discuss the differences between C3 and C4 grasses. Why do we care? I'll turn it over to you, Megan.
Thanks, Tim. Okay, so today we're going to talk about C3 versus C4. And when my 10-year-old asked me this morning what I'm speaking about, I told him, and he said, "What is that?" And I said, cool season versus warm season grasses. And he's like, "Why didn't you just say that in the first place?" It's like, good point. That's a good point. We kind of complicate it with these names, but I hope by the end of this that you feel really comfortable understanding why they're called C3 versus C4. So first of all, we know we have different growing seasons in Texas, and luckily we don't get too harsh of even winters. And so we have the opportunity to have a very high diversity of plants in our state. The warm season grasses, which I think we're probably all a little bit more familiar with, those are the C4 grasses. They're active in late spring. They go dormant in mid-fall. And then during drought, and they're very drought and heat tolerant. And so that's why we have a lot of C4 grasses that we utilize on rangelands. They have very deep roots, like George showed in a picture earlier, fantastic. They're able to reach some subsoil moisture. And so they're not at risk of dying off when we have our intermittent droughts, which feel like they're a little bit more than intermittent lately. Some examples that you're probably familiar with, our very own Texas grass, Cydotes grama, big blue stem, Indian grass, all the big grasses people talk about, but also a lot of the mid and short grasses. They're also warm season grasses or C4 plants. Now, C3 plants are cool season grasses. Those don't go dormant in winter. Instead, that's sort of when they start to come about. They go dormant when we get really hot. So just here in the past couple of weeks, we saw a lot of our Texas winter grass, wild ryegrass start to kind of phase out as our warm season grasses sort of started to thrive. And so that's the reason. Cool season grasses are going to do better at cooler temperatures. Warm season grasses really hit their niche when things get hot. So first I want to cover photosynthesis, because the C3 and the C4 have to do with the different ways that these plants conduct photosynthesis. So basically, if you think back to maybe 6th grade, I hope you were all paying attention in 6th grade. In 6th grade or so, we learned about how light hits those leaves of the plant. Those leaves are big solar panels. So that chloroplast in there, that's generating a lot of usefulness, where they take in the carbon dioxide, they take in water for the plant, and they're making glucose or sugars or carbohydrates that plant is using for a lot of its functions. And plants, of course, give off oxygen. So that's why people say it's great to have plants even indoors, because they're taking a lot of the carbon dioxide that we breathe out in. That's what they use, and they let oxygen off, which is what we use. So it's a really great symbiotic relationship. But that's the basis of photosynthesis, how light going onto that leaf turns into carbohydrates that the plant can use. So what is with the numbers C3 and C4? So first of all, I made this C3 very big, and I made this C4 very small. And that's because despite in Texas us having a lot of C4 plants, because we are generally hot and dry, the amount of C3 plants in our world is way higher. I'm talking like 85% or so of plants in our world are C3 plants. And maybe only a few percentage of our plants are actually C4 plants. Now, there's another category I'm not talking about today, but that's our CAM plants. Those are like our cacti. So this isn't including everything, but these are the two major differences in grasses that we're going to talk about. So C4, not quite as popular worldwide, but here in Texas, we have a lot of them and we appreciate them. So they have different photosynthetic pathways, or the way that they are able to generate the food for themselves. So C3 actually have 3 carbons in their chain. That's where the C3 comes from. Not very creative, right? This is our standard pathway. So a lot of people believe that all plants were C3, and some plants have become adapted to a C4 photosynthetic pathway in order to be more competitive in these dry, hot environments. But the basis are C3 plants. And that's probably why 85% of our plants on Earth are C3. Now, the C4 has one more carbon atom. So they create this carbon chain of 4 carbons in the initial process. And so this will come to be very important, because they are delivering these carbons directly to the source for where they need to go. So the carbon dioxide goes straight to where they can start to process it. Instead of in the C3 plants, they kind of bring it in a more inefficient way. And it has to come in through the stomata that are on the leaves. They're open. And so sometimes they kind of mess up, and they'll bring in oxygen accidentally. And so there's a lot of really bad dad jokes about photosynthesis that talk about how C3 plants are kind of, blondes where they forget and they bring in oxygen every once in a while. And this makes their whole photosynthetic pathway a little bit less efficient. Okay, so why is C3 not as efficient? The Rubisco, those fix the CO2. But then they also do this silly thing where they accidentally fix nitrogen about 20% of the time. And as a result, they have to push that back out in photorespiration. And so this photorespiration is very energetically expensive. And so C3 is considered not as productive of plants as C4 because they kind of have this little hitch in their get up to where sometimes they're actually having to get rid of the oxygen because that actually comes in at the same time because their stomata are always open. Now the CO2 comes in via the stomata, letting water vapor out. So there is this whole process to where they're just doing extra basically than what our C4 plants have adapted to do. Now, how is C4 more efficient, right, compared to that? They have this PEP enzyme that fixes the CO2 and makes that 4-carbon chain. And so they avoid bringing in oxygen molecules altogether. It's like they just skip that step of having to do photorespiration to get rid of that. They use bundle sheaths, which are located kind of on the outside and sporadically on the inside of that leaf to deliver the CO2 straight to that Rubisco that we talked about earlier. So they're saying like, here, Rubisco, this is our carbon chain. So they're a lot more efficient. They're not dealing with the oxygen. They can fix carbon even while their stomata are closed. Big advantageous characteristic of these plants. So C4 warm season plants can actually keep their stomata closed, keeping their moisture in, not losing everything to the environment, and still carry on photosynthesis. So pretty cool. So how do they stack up? If we were in an environment that was very carbon rich, right? And we had moderate temperatures and adequate moisture, our C3 plants would actually kind of dominate because C4 plants are slowed by the complex metabolism because they're actually having to make the chain and then take it there with that PEP enzyme straight to that Rubisco. So they have a little bit of an extra step. And the fact that C4 can kind of adapt to hotter environments and the fact that we're seeing some evidence of climate change happening, there are scientists actually working on taking some C3 plants, specifically crops, and changing those into C4 plants, which I think is super cool. They're trying to actually change their photosynthetic pathway in order to make them more efficient. All right, so C3, those cool season plants, they are best at about 60 to 75 degrees Fahrenheit. So that's when they thrive. They are the top dog during those cooler temperatures. They also love cloudy conditions. They do well with good moisture. So when we have those characteristics, we see a lot of our C3 plants thriving throughout the winter and springtime. This includes wheat, alfalfa, ryegrass. Many of our trees are C3. Texas wintergrass, little barley, cocklebur, rescue grass, Scribner dicanthus. Many of our thistles, there are some that are warm season, but many are cool season where they have their rosettes splayed out during the winter. And then when it starts to get warm, they're done. They shoot that stalk up and they kind of play out for the year. C4 plants, they're best from about 80 to 95 degrees. So the weather that we're having lately is key for C4 to do really well. So they are able to grow very quickly and grow high amounts of forage, which is awesome, but it may not be at the same quality as our C3 plants. Nevertheless, they are able to grow lots of forage. These are going to be like our corn, our sorghum, big blue stem, Bermuda grass, Cytoscrama, eastern gama grass. Most of the natives that we plant are in fact, C4 plants. They're very good at water conservation. These plants can do well on very little water with their deep root systems and their ability to close their stomata when things get hot. So finally, I want to end with why should we care that we have C3 versus C4 grasses? And I'd like to argue that there's a lot of reasons that it matters to us. And we're going to hear in our next presentation about why mixing it up, diversifying to fit your operation, and providing forage at different times of the year is incredibly important for livestock. It's also incredibly important for our wildlife species. They don't stop eating during the winter. And so there are some seeds that are being provided at different times throughout different seasons that's providing them some nutrition. We also know that C4 plants tend to be more water efficient, as we just talked about, while producing large amounts of forage. And so those are plants that we're probably looking at for our lawns, like we just heard about, for our pasture grasses, and thinking like how our temperatures are starting to increase all the time and our water is not necessarily a given. Those things are high considerations for when we're replanting or when we're thinking about strategizing what to put either on a landscape or on our rangelands. So again, choosing the right plant, fitting plants to their environment. And if you don't understand why one plant functions differently than the other, then it's very hard to figure out which ones are best. And finally, I'd like to argue, because you are all fellow plant nerds, that it's for this greater understanding. As we move into the future, we're understanding climate change and how those are going to affect our plant populations. We're understand why plant breeding could be very valuable. I know some people don't like GMOs, for example, but those genetically modified organisms may actually be able to take C3 plants and make them C4 plants so that they can withstand the hotter, drier conditions that we seem to be having more frequently. And then finally, knowing what to expect from plants is huge. So knowing that certain things are going to play out. For instance, I've been working with a field that has been taken over by thistle, but that thistle is finally dying out and a lot of our warm season grasses are starting to come on. And so it's really cool to watch C3, C4 combinations play out in real life. And so you see that those thistles were doing their part. They're holding the soil where there was no plant established well. And as they start to decrease, then these C3 or these C4 plants start to come up. They will eventually seed out, add seed to that soil, and hopefully produce new plants to fill in. So these whole ecological processes that we live in, those are built around our ability to understand how those plants thrive and how they thrive best. So that's why I feel like we need to know the difference between C3 and C4 beyond just calling them warm season and cool season plants. So of course, you know how to get a hold of me. You've all received emails from me, but you're welcome to email me if you have any questions about that. And of course, also find more information on my website or on our Facebook page at Texas Range Extension.
All right, so up next we have Lee Knox to speak on grazing warm season versus cool season grasses. Lee was with USDA NRCS for over 20 years before taking a role with Texas Christian University as a professor in ranch management. Prior to NRCS, he worked as a county extension agent for Texas A&M AgriLife Extension. Lee received his BS in range from Texas A&M University and an MS also in range from New Mexico State University. His extensive firsthand knowledge about managing rangelands, and we're so happy to have him on our plant party today. He'll be presenting on rangeland, warm season versus cool season grasses. Lee, I'll turn it over to you.
Well, good morning, everybody. I appreciate the opportunity to speak. I know I'm following Megan, and this is a pre-recording, but I do want to sincerely thank the coordinators in letting me present today. I enjoy doing these presentations. So they asked me to talk about warm versus cool season grass grazing, and so we will get to that. The reason I'm recording is I am at the Texas Section Youth Range Workshop, and it is prescribed burn day. If you do have a child that is a high school age child that's interested, or a grandchild that's interested in natural resources, look up the Youth Range Workshop, and it's a great week, always spent in June, and has been for 71 years at Junction America. And then so the other thing is I always have to do a little sales pitch. I am a associate professor of professional practice at TCU Ranch Management Program. And the reason I'm there wholeheartedly is because of our mission statement. Our legendary program, which is started in 1956, prepares professionals to manage a broad range of global resources than the ecologically sound basis while conserving and improving resources. So that ecologically, economically, and conserving are very important to me individually and professionally. So with it, let's just talk a little bit about the differences between cool and warm season grasses. I'm sure you got a good baseline education between C3 plants. Remember, those are the cool season plants, and the C4 plants, which are the warm season. CAM plants in this chart here, and this is the only time we're going to talk about it, those are the cactuses. If you look at this chart, the first thing you notice is the C4, the warm season plants, they have their photosynthetic rate can be upwards of twice or really a third more productive. Their photosynthetic rate be a third higher than C3 plants. However, if you notice on this chart, if you go to the bottom end, below about 40 degrees Fahrenheit, there is no production in C4 plants. They cannot photosynthesize below 40 degrees Fahrenheit. But their ability to photosynthesize and their optimum range, if you look, is really warm. And they exceed production of a C4 plant somewhere around 70 degrees Fahrenheit. So then when you look at the C3 plants or the cool season plants, what you see in that scenario is you see it has a really broad production potential. And so it essentially can produce, it can photosynthesize from freezing 32 degrees all the way up to 110 degrees Fahrenheit. So they have a really broad range, but their level and their rate of photosynthetic rate is just not as high as C4 plants. How about water efficiency? This is strikingly different. This is really important from a water conservation standpoint and a forage management standpoint. And from this chart, now these are agronomic crops, but it's fine. It holds true with forage crops. So the C4 plants, in this case, corn and sorghum, for every kilogram they produce about 0.00345 kilograms of biomass per liter of water. So if you rate that at 100%, you turn around and you look at wheat and barley at the same, and for the same amount of water, they only produce roughly 60% of what a C4 plant can. So C3 or cool season plants, they produce much less per unit of water than the C4 plants. And that is very important from an irrigation standpoint or from a water use or water efficiency standpoint. I don't know about y'all, but I've spent my entire career on the edge of the desert. I always say the 100th meridian actually runs through our main lease ranch. And so because of that, we are always seem to be in a water deficit. So we're trying to manage as much forage production as possible on as least amount of water as possible. So you do see the competitive advantage of the C4 or the warm season plants from a water efficiency standpoint. How about light intensity? So what you see here is the chart on the left. We need to read that. That's the flux of CO2. So that is actually the fixation of carbon dioxide is higher with C4 plants compared to C3. So they actually fixate more carbon with light intensity. However, if you go to the next slide, and this is actually biomass production, they're essentially the same. There's really no difference. And so there's really not that big of a difference from a light intensity. And this holds true in the landscape. We typically think that we see more C3 plants in the shade, and they can work better in the shade, so they don't require as much light intensity. However, when you get them out to the full sun, they produce similar amounts of biomass even in the full sun, but they do fixate less carbon dioxide. So how does carbon dioxide levels impact this? So we know it's scientifically proven carbon dioxide levels are increasing in our atmosphere. And so that's a big hot topic. And so what we look at is how CO2 levels, carbon dioxide levels, how they would impact it. So here's how these charts work. The left is the biomass production. So that is, these charts are flipped from the previous slide. So this is how much growth in the plant is based upon where CO2 levels were before the Industrial Revolution and where they are currently. And so even currently, C4 plants produce, and that's a 25% increase in biomass compared to C3 plants. So that's 25% more forage at our current CO2 levels. Now that used to be larger. And so C4 plants or warm season plants are reducing their competitive advantage as we elevate atmospheric CO2 or carbon dioxide levels. How about this chart though? This is really, really interesting to me. And so this is actually the fixation of carbon dioxide. So this is actually converting CO2 to oxygen. And so what we see is almost twofold an increase in the ability to fixate carbon dioxide compared from a C4 plant compared to a C3. Now, why is that important? Well, if we're going to store carbon dioxide and take it out of the atmosphere and store it somewhere, and there's lots of ways that's been proposed to do this, C4 plants actually do a much better job of fixating or converting CO2 and letting off oxygen compared to C3 plants. And so just remember this, the very best plant we have to sequester carbon out of the atmosphere, or carbon dioxide out of the atmosphere, is a warm season grass, period, hands down. And that's the way it works. Now, remember, C3s is not, we have C3 grasses, but most trees, shrubs, forbs, they are all C3 plants also. So that warm season grass is the best plant we have to sequester carbon dioxide out of the atmosphere. So let's summarize a little bit. We'll look at how temperature impacts. And so what we see is cool season plants produce over a very large range from essentially 32 degrees all the way to 110. Even though 32 to 39, we call that dormancy, they are still actually photosynthesizing just at a reduced rate. But you can see how broad of a range they can work. Optimum range is in the 70 to 95. I don't know about y'all, but we're starting to get pretty regular 95 degree temperature days. Cool season plants are not photosynthesizing at their best rate now that air temperature is that high. Warm season plants are warm season grasses in 90 to 105, even 110, 120. It doesn't really matter. They're going to photosynthesize when it's hot. Cool season plants grasses are more productive than warm season grasses below 68 degrees Fahrenheit. And then production for warm season or C4 grasses is essentially zero once you get to 40 degrees. So what do they like in the atmosphere? Cool season plants are adapted to higher carbon dioxide levels and lower oxygen levels. Warm season plants are better adapted to low carbon dioxide levels and higher oxygen levels. Optimal sunlight, it just doesn't matter. Both plants, they need sunlight to photosynthesize. And so there's really no big, large impact from a sunlight intensity standpoint. Water use, remember that 60%. Warm seasons use 60% as much water as a cool season plant per pound of production. Much, much more efficient with water use. Now to the two grazing differences. So what we see is the cool season plants, because they store less carbon as structural carbohydrates in those plants. Structural carbohydrates are less digestible. And so what we see is cool season plants are 13% more digestible than a warm season grass. They also typically run 6% higher in crude protein. So that makes it a much better feed source for livestock. Now, how does that counteract though is, as we do know with warm season grasses, we produce 25% more biomass at current carbon dioxide levels. So that you produce more warm season grasses, but it's less digestible than the cool season grasses. So as we go to a production scenario, what we really need to do is match our kind and class of livestock to the forage that we have. And so this slide here depicts it, I think, perfectly. What we have here is a set of probably 550, 575 pound, what we commonly call a yearling, or these are weaned calves, stalker calves. And so we typically will run those because their digestive system is not at full capacity yet. They do not have a completely developed digestive system. We run those on our better quality cool season forages, where it's 13% more digestible and the crude protein is higher. They also have a higher crude protein requirement in their diet because they're still growing. Just like our kids, you got to build skeleton, you got to build muscle. You need more crude protein to do that. And so we're going to put the cattle with the higher nutritional demand on those cool season grasses. Those cattle, those steers right there, they are set to gain anywhere between, they're going to average in today's livestock genetics, somewhere between 2.25 and probably 2.65 pounds of gain per head per day. And so pretty substantial. However, you cannot have those high growing stockers or yearlings without producing calves. And so what we have in the next picture here is we have a picture of a really nice red Angus cow. Her rumen, she probably weighs, I'm guessing, she may be a 1,200 pound girl. She's pretty moderately framed. She's short ribbed. She may be more like 1,100, somewhere in that ballpark. But her rumen is the size of a 55-gallon drum. And so that thing can digest fibrous, coarse materials really well. All her rumen needs is 7% crude protein in her diet for that rumen to function correctly. And so she can graze those warm season grasses, which have more structural carbohydrates, and she can actually digest more of those structural carbohydrates because of that great big rumen. She converts that to a very high quality, high crude protein, high fat product called milk for that calf right there that she's raising. And what we need is those C4 grasses produce 25% more at our current CO2 levels than our cool season grasses, and produce 25% more and convert that rougher, coarser material into milk into maintaining herd. So from a grazing management standpoint, it's typically what we see. We put our cows on our tougher country, warm season kind of country. And then what we typically see is our high value gaining cattle that need better diets. We put them on our cool season grasses to grow out and do better. So from a grazing management standpoint, where do we stand? Grass is grass. They all respond the same, no matter whether it's a cool season or warm season. It all respond the same to grazing. There's competition for where those carbohydrates are allocated in that plant. So from that, I'll bid you well, and I appreciate again the time I got to spend with y'all today.
All right. Thank you, Lee, for that presentation. Next up, we're moving on to turkeys and how they use grass structure. Jason Hardin is Wild Turkey Program Lead at Texas Parks and Wildlife Department. He's been the lead biologist for wild turkey since 2007. He received his BS in Forest Wildlife Management from Stephen F. Austin University, Arthur Temple College of Forestry, and MS in Range and Wildlife Management from Texas A&M University, Kingsville with Cesar Claiborne Wildlife Research Institute. Jason is the owner and manager of the Johnson Ranch in Leon County, Texas. Not surprisingly, he is an avid wild turkey and upland game bird hunter. Welcome to Plant Party, Jason. I'll turn it over to you to tell us all about grass structure needed for prime wild turkey habitat.
Great. Thank you, Megan. Good morning, everybody. Megan and Tim invited me to talk today about grass structure for wild turkey habitat. And this presentation is timely because we're right in the middle of the nesting and brooding period. So a lot of our hens are either incubating eggs right now or running around with their poults, hopefully. This is the most crucial time of year for wild turkeys to rebuild and grow their numbers. Well-managed grasslands, rangelands, pastures, and hay meadows provide critical nesting and brood cover for wild turkeys. And the structure of these habitat types can be the difference between growing or declining resident turkey population. And wild turkeys are found in most of Texas, and while habitat types change as you move from east to west across the state, the structure of good habitat remains the same. And when I think about habitat management for wild turkeys, managing herbaceous openings is a top priority. When we target a species for management, we're making purposeful management decisions. When we consider what is limiting on the landscape around our property, and then try to manage our property to make it more desirable for that target species within that landscape. So what is purposeful management? So when I think about purposeful management, I'm making decisions to impact that species. And three main items that I want to target are food, water, and cover. And we'll address all three, but cover is the most important and the structure of that cover. So food. Wild turkeys aren't picky. If they can catch it, swallow it, they'll eat it. Open grassy areas have the potential to provide a lot of benefits to wild turkeys from a forage standpoint, but two critical forage items jump out at me. First is that early flush of greens that appear in open fields during late winter and early spring, assuming that we're not in a drought. These early greens provide wild turkey hens their first opportunity to start building fat reserves in preparation for the upcoming nesting season. Wild turkeys graze on these greens just like cattle, and the later those greens appear on the landscape, the later your nesting season will actually kick off. And shortening that nesting season, actually due to delayed green up, will actually reduce the amount of opportunity your hens have to recruit poults into the population for that year. So we'd like to see a nice early green up to really get things kicked off. The second crucial forage item in these open grassy areas is an abundance of insects. Insects are attracted to and more abundant in open fields relative to forest settings. Insects are essential to providing the protein necessary to promote egg production and to grow flight feathers for poults. And without those insects, wild turkey numbers are going to decline. And it's not just having those insects on the landscape, but access to those insects. And that's where structure comes into play. There can be a ton of insects on an acre of open habitat, but if the young poults cannot access those insects due to heavy thatch or dense grasses, then we're not realizing the potential value of these open habitats. Habitat structure, particularly bare ground, with a canopy of grasses and weeds, like that seen in the photograph on the right there, allows poults to access insects while at the same time providing poults cover from their many predators as well as thermal cover. So water. Water generally is not a limiting factor for turkeys, especially in the eastern half of the state. But that said, during extreme drought periods, water can be a limiting factor as one moves west across the wild turkey range in the state. But in my mind, the most important aspect of water for wild turkeys is roosting habitat. And no matter where you are in Texas, from the piney woods all the way out to the high plains, wild turkeys generally roost near water, particularly adjacent to streams, creeks, and rivers. And this behavior isn't because they're there to drink the water, although they will drink the water, but that's where your biggest trees are on the landscape. And wild turkeys want to roost in the tallest trees available. And in some parts of Texas, the absence of roosting cover is the most limiting factor for wild turkeys. Openings adjacent to these roost sites can serve as launching and landing pads for wild turkeys as they enter and leave their roost sites, providing long linear openings immediately adjacent to tall trees along riparian areas is a great management strategy for wild turkeys. These linear openings should be maintained mostly in short grasses to allow turkeys to see approaching predators. Once grasses become taller than a turkey's head or too dense, wild turkeys will stop using them. Management strategies for these long linear openings may include a combination of fall and winter mowing, burning, and cool season food plots. Should avoid management actions early in the morning and late evening when turkeys are returning to or leaving their roost sites, and avoid management activities during nesting and brooding periods from April 1st to the end of July, or as long as you can go. Now for cover and structure that cover. So this is what is the most important thing for turkeys, in my opinion. So like most galliforms, your pheasants, your quail, wild turkeys are going to nest on the ground. A hen will roost in a tree every night from the time she's about 2 weeks of age, when she can first fly, until she finally starts incubating her own eggs. The nesting season is the most dangerous time for a hen, and to be successful, a hen will nest on the ground all night, every night, incubating her eggs for 28 days straight. This behavior results in the highest annual mortality for hens, but it's necessary to sustain and grow the population. Providing a quality nesting cover will improve nest success. Simply put, nesting cover consists of 20 to 30 inches of vertical cover consisting of grasses, weeds, vines, down treetops and limbs, and short shrubs. Nesting cover is typically thicker than brood cover. A study in South Texas found that wild turkeys prefer to nest in areas that have been deferred from grazing and have denser herbaceous cover than what might be found randomly. I believe these findings may have been part of Dr. Clayton's master's work, not 100%. Unfortunately, nesting hens often select the edges of hay meadows for nesting cover. And the timing of many of these haying operations overlap with wild turkey nesting season. This overlap results in approximately 12% of wild turkey hen nests being lost annually to mowing and haying activities. I hear about nests destroyed by haying and mowing operations every single year. Only about 30% of nests are successful on average before including nests lost to mowing. So losing that additional 12% of nests by human-caused activities, especially through mowing during the nesting season, can be the difference between a local population either growing or declining. So now let's talk about brood cover. Unlike many birds that hatch out featherless, wild turkey poults hatch out fully feathered and leave the nest within 24 hours of hatching. The poults follow their mother on the ground, searching for insects. Again, those poults can't fly until they're about 2 weeks of age, and insects are a critical part to providing the protein they need to grow those flight feathers. Due to their vulnerability in the first 2 weeks of life, only about 30% of poults survive to be recruited into the fall population. Unlike nesting cover, brood cover typically consists of scattered grass clumps, less thatch, more forbs, and more open ground. While nesting hens prefer that deferred pastures deferred from grazing, the broods want to move right next door to those pastures that have been recently disturbed through grazing, burning, or some other management activity. And they're usually going to be dominated by sparse cover, weeds, and more bare ground and annual grasses. Pastures dominated by native warm season grasses and forbs make much better brood cover than exotic grass pastures. These bunch grasses allow for easy travel between grass clumps, whereas most exotic pastures are dominated by side-forming grasses that reduce access to bare ground, which slows the movement of young poults, making them more vulnerable to predators and reducing their access to insects. These are flightless poults. A few things jump out at me in this video. First, you can't see the poults until they move. The vegetation is tall enough to hide the poults and short enough for the hen to see the oncoming threat. Second, I see a lot of bare ground, allowing this brood to move easily and navigate this vegetation. Broods typically utilize the edge of openings adjacent to woody escape cover. The openings provide ample supply of insects, and the woody edge provides quick escape from predators. If you need to target areas to manage for wild turkeys, can't commit to your entire property, the edges of where your woody cover meets your herbaceous openings is a great place to start. Older broods cover more area and begin to outsize many predators like snakes. The odds of living to be recruited into the wild turkey population increase daily as poults grow and develop flight feathers. Did you notice all three of these videos had a significant percentage of bare ground mixed with the herbaceous cover? So spring and summer are the most critical time for sustaining and growing your wild turkey population. Providing herbaceous cover boot high to knee high, April through July or longer, will be helpful to hide your nest from predators, to hide poults from predators, to provide that shade and thermal cover. I think George mentioned very high 100+ degree temperatures in that short vegetation versus being in the shade of that herbaceous cover. And this is also going to attract bugs, which are crucial for those poults. Manicured pastures are oversimplified landscapes that provide no nesting or brood cover. And while adult turkeys can use these fields with no problem, you don't get adult wild turkeys without first having a successful nest and recruiting poults into your population. Heavily grazed pastures are again sufficient for adult wild turkeys, but our management objectives should first be to create the habitat condition that promotes successful nest and allows poults to reach the stage where they can fly to escape predators. A good rule of thumb on the height of grasses and weeds is shorter than the hen, but taller than the poults less than 2 weeks of age. And remember that a diversity of plant species provides a diversity of insects, and in the fall of the year, these plants provide a diversity of seeds that can be consumed by wild turkeys and other birds. The site in this photo received a prescribed fire during the winter and was subsequently grazed, and for good measure received a few early spring dish trips. Setting back succession is a critical management activity, especially in the eastern half of the state where we get more rainfall. Open grassy areas managed for wild turkeys should be set back to bare ground on a frequent basis. Going back to bare ground through one or a combination of management strategies such as prescribed fire, grazing, and disking will improve the structure of the grasslands, remove thatch, promote weeds, and increase bare ground. This field is being purposefully managed to serve as wild turkey brood cover. The best predator management is proper habitat management. More usable space means more nest sites, more brood cover, and more habitat complexity for predators to deal with in their search for prey items. In addition, wild turkey habitat management will result in more rabbits and rodents to serve as alternative prey species. I like to look at turkey habitat as those areas you can see yourself easily hiking through. If you cannot see yourself walking through an area because it's too thick, it's probably too thick to serve as good turkey habitat. This is a photo of Yaupon holly choking out the understory of a forest in Leon County. No one wants to walk through a mott of Yaupon holly, and neither does a wild turkey. Increasing usable space is the only way to create, sustain, and increase the level of carrying capacity for wild turkeys. Usable space is simply habitat a wild turkey can utilize. A wild turkey prefers to walk rather than fly, and its primary defense against predators is excellent eyesight. To survive, a wild turkey needs to see predators coming with enough time to evade them. So for wild turkeys, usable space for those areas on the landscape that they can see and move through easily. Pretty simple. These woods were burned in February. The growing season following the burn produced excellent herbaceous cover in the forest understory that can now serve as nesting cover, brood cover, access to forage such as acorns and low-growing greens. It's going to be more attractive to insects. The open nature provides wild turkeys the ability to see predators and easily escape them. I assume you can, see yourself hiking through these woods, so it's a good example of wild turkey habitat. And just like the pastures and the fields in the earlier slides, this forest understory is taken back to bare ground every 2 to 3 years with prescribed fire. Burning maintains this open forest understory and creates an aesthetically pleasing landscape, at least for me. If fire were removed from this forest stand, it would return to a mid-story Yaupon holly, so maintenance of your woods is important. The following slides are a forest photo point in Leon County going back to 2007, and the photos go through 2024. We burned it this past year too, but I didn't include that photo. And it shows how incorporating prescribed fire can change the forest structure to benefit wild turkeys and other species. In 2007, this forest was choked with Yaupon holly with very little grass in the understory. In 2008, we burned the right side of the woods, top killing some of the Yaupon, letting sunlight reach the ground, and we started converting our fuels for future burns from just leaf litter to grasses and leaf litter. By 2012, we'd burned both sides of the road, top killing that Yaupon, again increasing light to the forest floor and promoting herbaceous cover. Over the years, we've continued to incorporate fire into this landscape, and now you can see the Yaupon holly it's still present, but it's in that short structure, very usable, lots of grass, so we're producing nesting cover, brood habitat, and usable space here. And we've just continued to burn it throughout the years. Again, we've converted more to a grassy fuel base rather than a leaf fuel base, so fires are even easier to carry now, so we're in more of a maintenance phase than we are in a restoration phase in these woods. And this is 2024. And while this is a forest setting and not open pasture, we are providing a ton of grass in the forest understory that serves as not only fuel for future burns, but shade for livestock. It provides nesting cover, brood cover, grazing for livestock, and we're increasing usable space for wild turkeys and many other species, including many species of greatest conservation need, all in this one management unit. So some important things to remember about purposeful management for wild turkeys. Consider delaying your mowing activities outside the nesting season. I'm sure all of you have heard of No Mow May, but maybe it should be No Mow May, June, July, and as long as you can go. Consider small management units or smaller management units. We see a lot of areas, 1,000+ acres being burned at a time or in one sort of a management strategy. I think a 500-acre management unit is about as large as you really need to go. Consider incorporating prescribed fire into your management activities. Fire may be the best tool for wild turkeys, especially in the eastern half of the state. Consider managing grasslands in a way that provides a diversity of habitat structure, ranging from openings deferred from grazing or fire immediately adjacent to fields recently disturbed with these same practices. So have that crazy quilt kind of approach. A lot of different structure out there is going to be helpful. Keep your management area diverse. Everything being managed the same way is just boring. And finally, monitor your progress. A 20-year data set of photo points helps you realize the impact you're having on the landscape that you're managing. In the end, our goal is more turkeys on the ground through production, that's nesting and nest success, recruitment through poult survival, and sustainability and growth by increasing usable space. And improving wild turkey habitat will improve habitat for many other non-target species. That's all I got.
That was great, Jason. Thank you.
All right. Thank you, Megan. Well, we're ready to get our last presentation started, and our final speaker is Dr. Jay Weeks. Dr. Weeks is the Vice President of Data and Soil Science at Grassroots Carbon, where he leads the company's soil science and ecological modeling team. In this role, he manages the data collection and quantification systems used to measure and verify carbon sequestration across U.S. grasslands. Jay got his start growing up on his grandparents' dairy farm in upstate New York. He earned a bachelor's degree in agricultural sciences from Cornell University and a PhD in soil and environmental chemistry from Kansas State University, where his research focused on phosphorus fertilizer, fate, and transport before building carbon crediting and supply chain emission programs at Indigo Ag. Today, he'll dig into the soil science behind one of the most powerful and underappreciated carbon sinks we have, well-managed grasslands. Take it away, Dr. Weeks.
Thanks, Tim, Megan, and the Plant Party team for having me. It's a real honor to have the opportunity to speak with you all and share a little bit about how good grazing management can contribute to improving ecosystem services and store soil organic carbon. I'm sure many of you already know grassland science well, especially after the great previous presentations. So by bringing the soil and carbon project developer perspective to this talk, my hope is everyone can take a little something new away. I'm a big proponent of first principles, so whenever I give talks like this, I try to offer a conceptual framework that lets the underlying mechanisms explain the results. Because soils and ag systems are so diverse and context specific, I find that trying to memorize any one detail is mostly just an exercise in frustration. For a long time, the field pictured soil carbon storage almost like a vault. You put carbon in, you shut the door, and it stays locked in complex chemical forms resistant to degradation. The more modern view, pioneered by scientists like Marcus Kleber and Johannes Lehmann, is almost the opposite. Nothing in soil is permanent in that it is locked away in a single form forever. In reality, the soil is best characterized as kind of a flow-through reactor. Carbon is constantly flowing in the form of roots, exudates, dead plant material, etc., and constantly flowing back out, mostly as CO2 as microbes breathe it away, and some, of course, is also lost by leaching or erosion. What's actually in the ground on any given day is the balance of those two flows. Persistence isn't really a property of an individual carbon-based molecule, it's a result of the system as a whole. An easy way to sort of think about building soil carbon that lasts is more like a reservoir fed by a river. Water flows through it constantly, yet the level can stay the same, lower, or rise higher depending on the rate of inflow and the height of the dam. Durable soil carbon is the same. What makes it long-lived is that it's continually replenished and the environmental conditions are such that it cycles more slowly than it's lost. That's what persistence really means here. Every practice you'll ever consider for your land does some combination of three things. It turns inputs up, slows outputs down, or grows the protected fraction. If we look inside the reactor for a moment, the soil community generally talks about two main pools of soil organic carbon. The first is particulate organic carbon, or POC. This is the larger, more recognizable plant material you might see if you scooped up some soil, some surface soil in your hand. It's things like chopped up leaves and stems or dried manure or other partially decomposed litter. It cycles relatively fast, generally on the order of years to a couple of decades, and it does real work. It feeds soil organisms and releases nutrients back to the soil. but it's also more vulnerable and responsive to changes in management, disturbance, drought, and erosion. The way POC hangs around longer is through physical protection. It can get trapped inside soil aggregates where decomposers can't reach it as readily. And this is one of the reasons a healthy, well-aggregated soil tends to build SOC. The second pool is mineral-associated organic carbon, or MOC. This is the fine fraction, generally composed of simple root exudates, microbially processed material, and dead microbes themselves. It's chemically bound to the silt and clay surfaces. It tends to cycle much more slowly. Radiocarbon dating often shows that MOC is far older than POC, and it's not uncommon for studies to find that MOC is century or millennia old. You'd think that the most durable soil carbon comes from the toughest, most decay-resistant plant material, the woody, high lignin stuff. And for a long time, that's what we assumed. It turns out that's mostly not the case. There are really two routes carbon takes into the durable mineral-associated pool. The first runs through the microbes, what people often call the microbial carbon pump. The high-quality nitrogen-rich inputs like manure or leguminous material that decompose fastest turn out to be surprisingly good feedstock for long-lasting soil organic carbon. Microbes eat them, it builds their own body mass, and then those microbes die. That necromass, the dead microbes, sticks to mineral surfaces as MOC. The second route is more direct. A lot of root exudates and dissolved carbon leach from sources like fresh manure can absorb straight onto mineral surfaces without ever passing through the microbe. The coarser structural material, like lignified stems, doesn't get as fully processed. It stays as that particulate POC fraction and is potentially shielded for a while inside aggregates. But if something were to break one of those aggregates open, microbes can and will eat it. There's a real debate about what actually drives how much carbon ends up in the durable MOC pool. One idea is that higher fungal to bacterial ratios help because fungal necromass binds well to minerals and supports aggregation. A competing idea is that the physical matrix itself, how much open capacity or empty parking spaces soil clays have, and how readily carbon can stack in layers on those mineral surfaces matters just as much as the traits of the microbes doing the work. Whether it comes down to the living workforce or the soil itself is genuinely still open, and the truth is honestly likely some combination of the two theories depending on the environmental context. Climate has a big effect on how fast the reactor runs. In humid systems, everything moves very quickly. High plant inputs are balanced by fast microbial breakdown. The priority here is getting carbon deep into the protected fraction before it's lost, using diverse, deep-rooted perennials and continuous cover. In more arid systems, like much of Texas, water limits both inputs and decomposition. We can't make it rain, but we can make better use of the rain we get. Litter and cover reduce evaporation and improve water infiltration, creating a virtuous cycle. Better cover captures more water, which grows more cover, which builds more carbon. I won't spend a lot of time on this slide, but it's worth knowing that not all clays are the same. The one-to-one clays, like kaolinite on the left, are tightly stacked with little internal surface area. They show up in older, more weathered soils. The 2-to-1 clays, like smectite, are younger, and they swell open like an accordion when they're wet. You often see these in soils that are like verticells, that cracking in dry clay soils. When they get wet, they expose a huge amount of surface area for carbon and nutrients to bind to. And that's the basic reason why two soils with the same texture on paper, whether it be from lab results or Surgo values, can behave very differently. It's the same building blocks, but different structure. If the protected fraction is where durable carbon lives, the practical question becomes, how much room does a given soil actually have to store more? It really comes down to three things. The first is what kind of clay you're working with. As we just covered, not all clay is equal. The expanding 2-to-1 clays like smectite have far more internal surface area than 1-to-1 clays like kaolinite. So pound for pound, they can bind a lot more carbon. The second is how much of that fine material is there. Capacity scales with clay and silt content of the soil. More reactive mineral surface, more parking for the carbon. But there's a catch. In almost every soil, there's a gap between the theoretical ceiling, based on what its texture would allow, and what we actually measure in the field. That gap is generally set by climate, the land's history, and current management. And that's really the room we have to work with when we're thinking about storing soil organic carbon. Yeah, and third, that's where the room is. Most of the unfilled capacity isn't at the surface, it's in the deeper profile. Deep grassland soils, in particular, tend to sit well below their ceiling, as you can see on the right, which is a big part of why depth matters so much and where the real opportunity is. So the soil sets the ceiling, but most soils are nowhere near it, especially down deep, and the headroom is exactly where good management is trying to fill. So how does this translate to grazing in the field? The same acre can go a variety of ways. Overgraze it, leaving the ground bare, and inputs collapse while losses climb, making that acre a net source of carbon emissions. Manage it well, and you build a protected fraction at depth, and it becomes an overall net carbon sink. One of the most helpful syntheses I've seen is from Paige Stanley and colleagues titled Ruminating on Soil Carbon, Applying Current Understanding to Inform Grazing Management. I'd highly recommend anybody who hasn't read it to take a look. They break grazing management into 4 levers that can be adjusted to suit conditions. Frequency and timing, meaning how often and when a plant gets grazed, and then duration and intensity, or how long animals stay and how much forage they take. Each of those dials maps fairly cleanly onto the 3 controls of the reactor that we've been discussing. So first, let's look at the input side. The goal is simple. Keep photosynthesis running hard and keep carbon flowing down into the soil. It all starts with green growing leaves. That's where the exudates and the labile carbon that feed the carbon pump come from. So the job here is to keep enough leaf area and enough recovery for plants to keep sending carbon into the roots and out through the exudates. Overgraze or let the animals come back and rebite before a plant is fully recovered, and you get the opposite. Leaf area can collapse, roots start to shrink, exudation shuts off, and you starve the engine that builds that durable mineral-associated carbon. This is what makes the adapted approach so different. It's less about how many animals you run and more about the patterns, how long they stay and how soon they come back. A short, intensive graze followed by real recovery lets a plant get bitten once and then rebuild. In response to warm season grasses, that moderate bite with enough rest behind it can even spur compensatory regrowth, holding productivity up better than continuous grazing would. But the rest is the bigger lever. Enough recovery lets roots grow deeper and push carbon further down into the profile, and it may tilt the soil community towards that fungal community that we talked about earlier that is thought to help root carbon into the more durable pool as well. Lever 2 is about where the carbon is coming into the system ultimately ends up. As we've been discussing, most of the mineral capacity for chemical protection sits deep in the subsoil. So the goal is getting carbon below, say, at least 30 centimeters. That long recovery period that defines adaptive grazing gives deep-rooted perennials and a diverse plant mix the time to build the root systems that deposit carbon at depth, which was nicely highlighted in some of the previous presentations. Depth buys you 2 additional things as well from a soil carbon perspective. One, the carbon is physically safer because it's buffered against disturbance events that churn the top few inches of the soil, such as erosion or in some cases tillage, but it's also biologically protected. The subsoil is much cooler, tends to have a lower oxygen content, and has a smaller microbial population, meaning that same molecule simply cycles slower, a meter down into the profile than it might near the soil surface. So a diverse, deep-rooted sward, given time to recover, is really a delivery system carrying carbon down to where the soil has the most room and the best conditions to hold on to it. Once carbon is coming in and going deep into the profile, lever 3 is all about protecting what's already there and slowing what's leaving. After addressing the basics of keeping the ground covered, not by overgrazing and removing the litter and leaving living plants on the surface that slow erosion, beyond that, microbes need more than just carbon to build stable organic material. Think of it like building a house. Carbon is the bricks, but nitrogen, phosphorus, and sulfur are kind of the mortar. When microbes have access to high quality material with a better balance of those nutrients, they use the carbon more efficiently, and more of it ends up locked onto minerals instead of being respired away. This is where managed density earns its keep. Concentrating animals for a short bout and then moving them onto the next paddock does 2 things a more continuously grazed pasture doesn't. One, it cycles nutrients faster and spreads them more evenly. Dung and urine return nitrogen and phosphorus in plant available forms across the whole paddock instead of piling up in a few of the cow's favorite spots, perhaps near a watering point. The thread through all of these, through all 3 levers, is the same. It's not really the number of animals. It's meshing the grazing and the recovery to how the plants are actually growing. Get that right, and you're turning all 3 controls at once. So putting this all together, you don't need to take my word for it. A picture here is really worth 1,000 words. Here's an image of one of our partner ranches from the air with the improved management on the left and more conventional management on the right. It's clear that proper stocking rates and adequate rest nudge all 3 controls at once. More carbon going in, less carbon going out, and more of it ending up being protected in that soil matrix. On top of that, you get better cover, improved infiltration, and better forage quality as well. But we won't be releasing any final numbers until later this year. I can tell you that the improvement in soil carbon in the system on the left has been clear. In the literature, the mechanisms I've highlighted are fairly well grounded in reliable data. If you're interested in reading more, please reach out. I'm happy to recommend a number of papers, many of them cited in this presentation. Many space for time studies comparing more conventional continuous systems to those using improved adaptive grazing, according to the levers we've discussed, find that soil organic carbon stocks are higher in the adaptive system. For example, Mosier et al. 2021 found that adaptive grazing held about 13% more total soil carbon and about 25% more in that durable mineral associated fraction, looking at 5 ranch pairs across the southeastern United States. The context-specific, system-level, and interrelated nature of adaptive grazing makes it genuinely difficult to study in a traditional experimental design. Additionally, historically, a lot of studies have only focused on that top 15 or 30 centimeters of the profile. I personally think that this has caused a lot of confusion as changes or lack thereof in the upper portion of the soil profile do not necessarily reflect what's happening in the subsoil, where we would expect more persistent SOC derived from deep-rooted perennials to accumulate. The 3M project being run by Noble Research Institute in conjunction with a number of organizations and universities, including Texas A&M and the USDA, is helping shed more light on this matter and is starting to present some encouraging early results from their Flux Tower sites as well. So I look forward to more of that data being made public in the future. The results we're collecting at Grassroots align with the literature as well. As a number of our ranching partners enter their 5th year of our programs, we are conducting the true-up measurements required by the carbon crediting protocols to ensure that the credits we have issued annually are reconciled against what can physically be measured in the field. We'll be releasing more information publicly later this year, but initial results generally reveal the expected pattern of MOC increasing relative to POC with depth, as highlighted on the left, and meaningful gains in SOC stocks. We believe strongly that research and carbon programs need to be sampling to a full 1 meter depth where possible to get the full profile picture of SOC dynamics, and a number of ranches are demonstrating why this is imperative. Had we sampled only 30 centimeters, some ranches would register no gains or losses even, instead of showing statistically significant increases in the full 1 meter profile. The figure on the right is illustrative, but highlights a pattern that we've seen on many ranches transition to adaptive management that optimizes the levers that we've been discussing. As more data comes in, we look forward to publishing and sharing more of those results with you all. So to wrap up, think of soil carbon as a flow-through reactor. The durable carbon is the portion we protect from being lost. The part we build through management into the mineral-associated pool at depth, where it has both the capacity and the conditions to stay. Soil and climate set the ceiling, but management determines how close we get to it. The good news is that the same practices that build the durable carbon also deliver better ground cover, improved water infiltration, and more stable, high-quality forage. We'll keep learning as more data comes in, but my contact information is on the screen, and I'm happy to take any questions. Thank you.
Thank you so much, Dr. Weeks. All right. Again, thanks to our door prize donors, Bamert Seed, InView Range and Pasture, Native American Seed, Texas Quail Forever, Renewable Resources Extension Act, Texas A&M AgriLife Extension Service, and the USDA Natural Resources Conservation Service. We appreciate your support of the Plant Party. Thanks again to all our speakers and to you for attending our 23rd Plant Party webinar. Again, Plant Party is a quarterly advanced plant training series brought to you by USDA Natural Resources Conservation Service, Texas Parks and Wildlife Department, and Texas A&M AgriLife Extension Service. We will be sending a short link to a survey by email, or you can type the address that you see in the chat box, or we'll pop up the QR code that you can simply hold your phone camera over and click the link that pops up. Mark your calendars. The next Plant Party is on September 16th, and we'll be covering Sedges Have Edges and Rushes Around. Stay quirky, Plant Partiers. We'll see you then.